So we're going to talk about temperature and heat. And in this chapter, this is the remainder of chapter 3. So I believe that these are all the notes you're going to need for chapter 3. That means that you have a test in chapter 3 coming up. I believe, I'm going to double check on the Web of Ren. Let's see.
It's the 30th, right?
Today is the 30th?
Yeah. I'm one day behind, but I didn't even know it.
I'm sorry. So I will double check. So yes, your quiz has been moved to Tuesday when we get back from the holiday. I forgot to tell A Block if you're celebrating the holiday. Happy New Year. So your test, I believe, is next Friday. But I want to double check so I don't give you bad information. Tonight for homework, you do have a Mastering Chemistry.
Is it a big one since we have 3 days to do it?
I don't know.
Sometimes those things.
Nope, your test is on Thursday of next week. So Thursday of next week is your chapter 3 test, okay? So make sure you write that down. Quick quiz on Tuesday, so it's not going to take a long time. We just have half the block to do it anyway. Then we're going to finish up talking about specific heat. So let's talk about matter and energy. Matter and energy. So what is matter?
Anything that has mass and not in space.
Perfect, and that's great because remember, this is included in chapter 3, so it's a good little review for your test coming up. So it's anything that has mass and takes up space. And keeping in that with that idea that we should probably look it over and think about it. What were the 3 states of matter you had to know?
Solid, liquid, and gas.
Fantastic. So I'm just going to write down solid, liquid, and gas. Remember that this unit, we also covered the different names of those phase changes. So you need to go back and you need to look over that phase change triangle for your test next Thursday. You need to know the behaviors of each of those states of matter.
Thursday or Friday?
Thursday, I said. And then with matter, we also learned the matter flow chart. That's this unit as well. So you have the different types of matter. So there's a lot of information in this unit. I would start making maybe like a Quizlet or just study a little bit every night and it won't seem so oppressive the night before. The other major component in the universe besides matter is energy. So what's energy? Max, you're my physics person. You've had physics. What is energy?
Isn't energy like how much you have to like?
No.
work?
Close. It's the capacity to do work. To do work. Well, then what's work?
Sort of like anything that requires effort.
No, it's not anything that requires effort.
Is it exerting?
It's not exerting. It's really weird because the definition of work is literally like the formula for it. So if you know that work is equal to FD, the definition of work is that it is defined as the result of a force acting on a distance. Remember that?
Can I watch the printer?
Totally, yo. Denida. So the definition of work, if it's hard for you to remember lots of words, if you can remember W equals FD, you should be able to extrapolate from that. So now we've got another law. Holy cow, you guys have the law of multiple proportions, the law of definite proportions, the law of conservation of mass/matter, and now for real, a fourth one this unit. Hold on, wait a minute. I just put another law in it. The law of conservation of energy. So what do you think the law of conservation of energy says, based on your previous knowledge?
Energy.
Not be created or destroyed?
energy cannot be created nor destroyed. So what happens to it?
Flows.
It's transferred. Very good, Lauren.
What? So in the rule of tens,
Mhm.
what happens to that 10%?
The 10% is passed on to the trophic levels above it. The 90% is what they say is lost as heat. It goes back into the environment. Yeah. So it's not like it just disappeared.
And then eventually goes into the food that the autotrophs eat.
It'll go back into to the universe to be used again by something else. So we're really all interconnected. We should hold hands and sing. What this means is that the total energy in the system, so the total energy is constant, but can be changed from one form to another. It can also be transferred from one object to another. So an easy way to think of this would be like turning it from one form to another. Would be like when you eat food, it takes, or even simpler, the autotrophs, or photoautotrophs, or photosynthetic organisms are going to take the energy in the form of sunlight, and they're going to transfer it into chemical energy stored in the bonds of glucose. You're then going to consume that glucose, break it down, and then you're going to transfer that energy from that chemical form into the form of ATP. Then you're going to use that to move your muscles, and you're going to transfer it into the form of that chemical energy into mechanical energy of you actually moving. It also says it can transfer from one object to another. That's like if you've ever played pool or billiards, when you hit the white ball and it hits the other balls, the white ball will, you hit the white ball moves real fast, it hits the other balls, and the white ball kind of stops and the other ones scatter. It's just the transfer of the energy from the cue ball to the other billiard balls. Probably the most classic example of energy transfer.
And is that why kind of all the balls go slower than the cue ball went?
Yes, because a little bit's going to be lost to friction. So what are the types of energy? The total energy of a sample of matter is the sum of all of its kinetic and its potential. I guess I should write energy. And its potential energy. What do we say kinetic energy is?
Like moving energy?
So kinetic energy, I'm just going to call it KE, is the energy of movement. And what is potential energy?
Stored energy.
Perfect. It's stored energy. And it is associated with either position or its composition. What that means is that in physics, when you were talking about potential energy, if we had, I'm sorry, it's really bad, that's my cliff. So if I have a rock on the top of this cliff that's not moving, and I have a rock on the top of this cliff that's not moving, both of them are not moving, so their kinetic energy is 0, but which one has the greater potential energy?
The higher one.
The higher one, because it's associated with its position. That's what they mean by that. Where it says its composition would be, let's say that you have eaten something that only has, you ate an apple today and that's all you've eaten all day. Or you've eaten a big plate of spaghetti and a couple of candy bars, and then you had an apple and a whole 2 liter of soda. Well, the big meal, its composition is greater. It has a greater propensity to provide energy for you, whereas the energy in the apple is going to run out because it's just far less.
So why is it that I tired and not willing to do anything after the ladder?
Oh, because your body's working on digesting it. Probably shouldn't eat all that in one sitting. It all has to come out. So that what is the SI unit for energy?
Joules.
Perfect. It's the joule. And that is a capital J. Another unit of energy.
Watt.
What? I heard you. No, I'm just kidding. Actually, the second most common one is the calorie. The calorie is a unit of energy. How many of you have heard of calories before? I should hope so. A calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. You should know that a calorie is larger than a joule. I feel a conversion factor coming on. You need to know that 1 calorie, little c, not call, is equal to, does anybody know the conversion for calories to joules, just out of curiosity? 4.184 joules. So that's your conversion factor. Remember, you can say 1 calorie over 4.184 joules if you need to, or you can say 4.184 joules over 1 calorie and use it as a conversion factor. So 1 calorie, besides being equal to 4.184 joules, is also related to kilocalories. I guess I can write it right here. Let's see, that's 4.184 joules. And so 1,000 calories is equal to what?
1 kilocalorie.
Perfect, 1 kilocalorie. Wait, how did you know that?
Because it has the K in front of it, and that's like.
Perfect, because you know your SI prefixes. So 1 kilocalorie is equal to 1 calorie with a big C. And that is what the food here in America is, food energy is measured in. So when you look on your food, so for example, this drink has 90 calories. Really what it has is 90,000 90,000 little calories, like calories with a little c. So we write it as just calories with a big C, and so we know it really is equal to a kilocalorie. Over in Europe, they don't do that. They write it out with the little c. So you'll go over there and something might have 14,000 calories, and you're like, holy cow, that's more than I should eat in a month. But really, it's just because we do our conversions for you silly Americans who can't do it on your own, I guess. So another unit of measure is the one that you're going to see in your on your electric bill is the kilowatt hour. And a kilowatt hour is measured as 1 kilojoule per 1 second times 3,600 seconds in 1 hour. So it's essentially 3,600 kilojoules per hour. And that is how, again, your electric bills come in the United States. But where does the idea of the joule come from? Well, the joule is a derived unit. What was the other thing that we had as a derived unit? Who remembers? Derived unit means it comes from a formula. What was another unit you had to know that came from doing a mathematical formula? So what units? No, not the moles. Another derived unit is, what is that a measure of? Density, very good. Where did you get your units from density? Doing the mass divided by the volume. So the joule is a derived unit. And the joule comes from, they call it Newton meters, which is really kilograms times meters squared over seconds squared. It's just where it comes from. So let's go ahead and practice doing some conversions. Calculators ready. It says a candy bar contains 225 big calories of nutritional energy. How many joules does it contain? What is your conversion between calories and joules?
1 to 4.18.
One what?
1 calorie equals to 4.184 joules.
So 1 little calorie is equal to 4.184 joules of energy. Very good. But I have 225 big calories. What does that mean?
That's 225,000.
Perfect. You know that 1 big calorie is equal to 1,000 calories. And then we know that 1 calorie is equal to 4.184 joules of energy.
Is the answer 941,400?
Oh no, I have to wait. And by the way, if that's the answer, you need sig figs. And because it's that large, what would you have to give it in?
Scientific notation.
Scientific notation. So,
Our sig figs could be
3. Very good. So what would it be?
9.41 times 10 to the 5th.
fifth. Yeah, you're right.
10 to the 5th what?
Joules.
Perfect. Real simple, basic calculation. Great job. We haven't done math in a while. I want to make sure you remember it. So yes, you will have to do a couple of these simple conversions, but more than anything, it's just getting swing of dimensional analysis.
So you can measure the energy in like a candy bar?
In joules that you would use in the lab, absolutely. You can just convert it. You can go home and look at the energy in a serving of cereal and see how many joules of energy it would be. Then you could actually convert those joules of energy into kilowatt hours and see how long it would take, you know, eating that cereal or breaking down that cereal would like power your electricity in your house.
Not that long.
Probably not that long. You're absolutely right. We're going to talk about the way in which they determine the calories. They use a calorimeter and they burn it off and they calculate the energy given off. And they know that the energy given off, because of the law of conservation of energy, must be equal to the energy that was stored. And so they'll use that process, and that's how they'll calculate the energy that's in your food. So everything you eat, that they've burned it in a special container to figure out how much energy is given off.
Wait, so could you like in The Walking Dead, could you set up a contraption where you could take all the dead walkers and burn them and just power your place? Because there's so many.
Eventually, yeah, you could, because there's going to give off energy. I mean, I'm not sure that I would want to be smelling that, but you know, I guess it's not nearly as
I should write
horrible
to them
as like
and be
sewage.
Have your smart guy come up with a contraption like this.
Like that's just basic science. So what's temperature? We have already defined it as what?
Measure of average kinetic energy within
You are so smart, sir. Average kinetic energy of the particles in a substance. So this means that the faster the particles in a substance move, the higher its temperature. But temperature can also be thought of as how hot or cold the object is. Why? Because that's indicative of the motion of those particles.
Is it like the faster particles move? Is that like,
The hotter it is.
does that like make friction? Is that what?
So could you use
No,
a
not- it doesn't make
pickup
friction.
line to be like, yo, your particles are moving at a really fast.
Yeah, or no, it's like, I think your particles are accelerating at a maximum velocity. Yeah. I'm sorry. We can also say that temperature is a measure of the thermal energy. Do you remember the SI unit for temperature?
Kelvin.
Perfect. It is Kelvin. Do you remember the equation associated with it? K is equal to C plus 273, and your book even wants to go further because they know you're smart enough, 0.15. 273.15.
Oh yeah, and then there was one for like Fahrenheit.
There's one for Fahrenheit to Celsius, but we rarely use it. So the temperature is measured in degrees Celsius, is what we use in the lab because we don't have thermometers that are in kelvins. Besides that, kelvins are really, really, it's hard to get into like 1 Kelvin. Your temperature in Kelvin would be really high. So we use Celsius in the lab. What do they use on the news for temperature readings here though? Fahrenheit, that other scale. And in case you don't remember, you are going to have to know the boiling points.
The boiling point in Celsius is 100, right?
The boiling point in Celsius, it's 100 degrees Celsius.
And for Kelvin,
It's
two,
it's 212 degrees Fahrenheit, and it is
375.
75. Wait, is
it would be 373.15 Kelvin. Notice we just write K and not degrees K. There is no degrees Kelvin, it's just Kelvin. You also have to know the freezing point or the melting point. So for
100 below for Celsius. It's 0 for Celsius.
it's 0 degrees Celsius,
32 Fahrenheit.
32 degrees. Look at you.
And 273.15 K.
And it would be 273 point, very good, 0.15 K. Look at you on the, just on fire and fuego. Your particles are accelerating at a maximum velocity. So let's do a practice conversion. It's real simple. You might not even need your calculator. Negative 25 degrees Celsius to Kelvin. What's my formula? K is equal to 273.15 plus C. So in this case, K is equal to 273.15 minus 25. And what do you end up with your temperature in Kelvin?
240.
Oh, just plug it in, Aaron.
253.
No, 248.
Oh my goodness, nobody can do mental math.
It's
248.15.
Yeah,
No, 248.
It's 248.15. He's right.
No, like 885.
Oh, 247.15. 247.
Just plug it in.
It's
247.85.
It's 247. No, it's 248.15.
Yeah.
240 what?
248.15.
No, 0.85.
Yes,
Yeah.
it's going to be 0.85.
Yeah.
Beck, will you plug it in?
Because you,
248.15.
273.15 minus 25. Oh no, they're right. Yeah, no, it's the other way around that you're thinking of it, Aaron.
Yes.
248.15 Kelvin. Yeah, you did it the other way. It's okay. How many sig figs should our answer have?
2.
It is not 2.
It's 1.
It's not 1. What is the process that we did to derive it?
Addition.
Addition, very good. And what is the rule for addition?
Behind the decimal.
How many behind the decimal? And
There are 0 behind the decimal.
there are 0 behind the decimal, so that means where is your first significant digit? In the ones place, right? So that means that your answer must go all the way to the ones. So what would your answer be? 248 Kelvin. So we need 3 sig figs. Why? Because of addition rules. Please make sure you remember that.
So, is that why you weren't having us do the 0.15? Because the majority of the time.
It's not going to make a difference, yeah. Majority of the time, it doesn't make a difference. So, but I don't want you to go home and do because you have a mastering chemistry assignment tonight. I don't want you to go home and not use the 0.15 because that's what the book uses and get it wrong. So, but yes, Aaron's absolutely right. Normally, I just say do 273 because generally speaking, you're given your temperature in Celsius as a whole number, which means that you're not going to have anything past the decimal anyway. On the other hand, you know that heat is a form of energy that not only takes into account the energy of the particles, but also the number of particles as well. So this one here depends on the amount. Would this be extensive or intensive?
Extensive.
Definitely. What did we call heat? Who remembers?
The transfer of the energy.
We had a fancy word for it.
Oh,
Sounds like you have a lisp. Enthalpy. Very good. What was our symbol for it?
triangle H.
Delta H. Very good. And if it was negative, what kind of reaction was that? Exothermic, which means what?
That it's going into.
Nope,
No,
that the
it's
heat,
exiting something.
it's exiting, so the container gets hot. Very good. And if it was positive, what was that? Endo, which means? It's entering, which means? The container gets cold. Very good. So the way that's easy to remember that enthalpy or heat, it takes into account the number of particles. It's based on the amount. So it takes more heat energy to bring a pot of water to a boil than it does a cup of water to boil. But whether it's a cup, a pot, or a drop, it's going to start boiling at the same temperature. It just takes longer because there's more particles I have to heat up. So that's the big difference between heat and temperature, is that the temperature just depends on the motion of the particles or the energy, and that heat is dependent on how many particles you have as well.
It's kind of like how when you're cooking something, like the outside can get burned, but it's still uncooked because it didn't reach the temperature on the inside.
That's why it's better to do it low and slow to allow the heat to go ahead and be transferred all the way into the center. Cooking is just chemistry. It really is. Cooking is all chemistry.
So what if you're a chemist cook? Does that mean
They call it molecular gastronomy. They do, and it's a whole big movement in the food industry. It's called molecular gastronomy. Look it up. It's great. There's a place downtown Chicago where they use like the liquid nitrogen to cool things down, or they'll use like the sodium alginate to like put yeah, and they'll use like sodium alginate and they'll flavor it, and so like instead of eating like your soup normal, you would eat it as in like flavored gel balls. So basically like a glorified jelly or gummy worm of.
Also like oxygen bars.
It's a big movement, molecular gastronomy.
Also like oxygen bars, right?
Yeah. I'm not going to pay for oxygen. All right, so when we are going to then use the information you already know, and we're going to we're going to then use the meaning of the joule, and we're going to show how we could go about solving for that energy.
This is going to be on the test.
This is on the test, totally. We're going to start solving for what we call specific heat. And you can also, for specific heat, you could also refer to it as the heat capacity, although most books refer to it and people refer to it as specific heat. So the specific heat is defined as the quantity of heat energy. What's the unit for heat energy? What did we say? J. The units in joules. That is required to change the temperature of 1 gram of a substance by 1 degree Celsius. What does that sound similar to? The definition of what?
The water.
The calories. Very good. So it sounds similar. So a calorie is only good for water. Specific heat is for any substance. But for this here, the specific heat, it's a constant. And it's based on the identity of a substance. So what does that tell you? Is that intensive or intensive? intensive
It's based on the
identity
not
of
the
a
amount, yeah.
substance. Oddly enough, the specific heat of water is 4.184 joules. The definition of a calorie is where it came from. Your unit here, it's another derived unit, so your unit is in joules divided by grams degrees Celsius. That is your unit. Oh. My question to you is, can you figure out
Joules over gram.
over grams degrees Celsius, which means joules over kind of like parentheses grams times degrees Celsius.
Okay.
So it's grams.
Grams of a substance times its temperature.
In Celsius.
You do that in Celsius, and then you divide joules by that.
Yeah, I'm going to show you. The formula for it is Q equals MC delta T. I know that's what everybody calls it. We're going to talk about what each variable stands for here in a minute, but since you can't wait, the Q is going to be the heat energy in joules. What do you think the M is? So this is going to be the energy. Perfect. So this is going to be the mass. And what do you think the mass is going to be in?
Grams.
How did you know that?
That's the SI unit.
Actually the SI unit's in kilograms, but it's in our specific heat. See here, this is the specific heat. And that's a constant. And we just said that the unit for that is joules per gram degrees Celsius. And delta T is going to be the change in temperature. How do you find the change in temperature? If I asked you to find the change in your hair length after a haircut, how would you do that?
You start with like
The initial.
what you had.
Well, it's final minus initial is how you find the change in temperature. Final minus initial. And your unit should be in degrees Celsius. So that's where that unit comes from, Aaron. So when you're solving for joules, you would see that if we're multiplying grams, it would be like G over 1. So this gram would cancel out. We're multiplying, it's like degrees Celsius over 1. This would cancel out with that, and you're left with your answer in joules. That's where the units come from. So if you look at a table of specific heats I took right out of your textbook, table 3.4, this has the specific heats for some substances. What has the highest specific heat on the list?
Water.
It's definitely water. What does that mean? What does specific heat tell you?
It tells you how much
Yep.
energy it takes to.
Perfect. It has a higher number. So what does that tell you?
It's gonna take a lot
It
of
takes
time.
Perfect.
energy to raise the temperature.
Perfect. It takes more energy
By like
to
one-
change
Isn't it about like 1 degree?
the
Celsius
temperature, of water.
per gram?
This is why it takes a lot of energy to get your body temperature to change. You guys are made primarily out of water. This is also what gives you that phenomenon where they say in the wintertime it's always warmer at lakefront. That's because it takes longer for the water to drop in temperature, and so that heat is radiating off and that thermal energy is being transferred into the surroundings. It's also why in the summertime it's cooler by lakefront, because the temperature of the lake hasn't risen to the temperature of the air. This is what helps your body maintain homeostasis.
So if we're cold, should we just like jump in the water and get warm up?
No, I wouldn't jump in that water.
'Cause then-
So why is it that like if you're in a lake and it's 65 degrees it's considered freezing, but if you're out in the air and it's 65 degrees?
It's different
Yeah.
because the water's going to start immediately trying to evaporate off of you, and so as it evaporates, it's taking the heat energy from your skin as well. So it's like sucking the heat out of you, because what is your temp? What is
Entire.
yeah.
Is that because it's like when you get out the water,
It's going to dry off. Yeah,
it's in
evaporate.
like a less amount than what's in your body?
Can you tell me which one of these things here? So let's look. Okay. Gold has a specific heat of 0.128 joules per gram degree Celsius. That's really, really low. That means that gold, basically, the heat. If you heat up a piece of gold, it's going to transfer that energy right away, and it's going to get very hot very fast. So when a substance absorbs the heat in Q, we said the temperature change is directly proportional. So the change in temperature is in direct proportion to the amount of heat absorbed. So in other words, the more heat absorbed, the greater the temperature change. Or the greater the temperature change. So more heat absorbed equals more change in temperature. This is basically where we're going to end. So we know that Q, again, is going to be our heat energy in joules. Our M is going to be our mass in grams, generally. The C is the specific heat. And that's in joules per gram degree Celsius. And we said that delta T is our change in temp. I do want to mention that sometimes your specific heat is not going to be given in joules per gram degree Celsius. Just like sometimes your masses aren't always given in grams. Sometimes they're in milligrams. Sometimes they're in kilograms. It's important for you to look at the units in your specific heat, because the whole goal is to get these things to cancel out. So if they give you the specific heat in joules per kilogram degrees Celsius, then you're going to have to obviously convert your mass to grams. Sometimes they'll even give it to you in joules per gram Kelvin. What would you have to do then?
Convert the Kelvin to Celsius.
Convert your Kelvin to Celsius to get them to cancel out. So you should pay attention to the units that you're given. It's going to help you solve.
Are we gonna
This will not, the homework tonight is on mastering chemistry.
What number
is
is
it gonna
it?
have this?
It's going to have, it's not going to have problems solving these yet because we haven't solved these together, but it's going to go up to the information we covered today, okay? And that is, I don't know, it's chapter 3, maybe like C or something. I don't know. You'll see it. It's due.
It'll be on
Don't forget that if you don't get at least an 85%, 2 days after it's due, which will be Tuesday, you will have that adaptive remediation that you have to do, okay?
I don't know what that means.
It means that there's another assignment you have to do afterwards. If you don't, it's a follow-up. If you didn't get at least an 85, then that tells them you need more practice. And so the computer will generate problems based on what you've gotten wrong so you can get better at it. Ask Aaron. He did that for anatomy. What was it in anatomy that you had to keep doing over and over and over again? It was the only thing you got wrong on the test.
It